Welcome back as we continue to learn more about inner products on vector spaces. We've seen that M22 is also a vector space under standard operations. So if we let U be the U matrix, U1, U2, U3, U4, and V be the V matrix, V1, V2, V3, V4, let's check to see if U inner product V, defined as the trace of U times V, is U1 V1 plus U2 V3 plus U3 V2 plus U4 V4 is an inner product. And just a quick reminder, so if we wanted to talk about the trace is the sum of the main diagonal elements of a square matrix. So we're going to multiply these two matrices, but since we only care about the main diagonal elements, I'm only going to do the 1, 1 and the 2, 2 positions. So we'll do the U1 V1 plus U2 V3. And for the 2, 2 position, we'll take the second row by the second column, getting U3 V2 plus U4 V4. And you can see that if we do the trace and add up those elements there along this main diagonal, we get exactly what we started with. So I want you to try and see if this is an inner product or not. And remember that to be an inner product, we have to satisfy all four axioms. And to not be an inner product, we have to show that he fails at least one axiom in at least one case. So take a minute, work through that, and then we'll come back together and see what you found out. Okay, so how'd you do? You might have tried checking axiom number 1 and found out that axiom number 1 does in fact work. So does axiom number 3. You can pull a scalar multiple out of everything. But when we get to axiom number 4, we need to make sure that a vector inner product itself always has to be greater than or equal to 0. I happen to pick a matrix here. I was looking for a way that I could maybe make this go bad. And so what if I make this be 1 and that be -1? And etc. And so we can show that this is in fact not an appropriate inner product for our vector space. So make sure you check all the axioms and either show that they always all work or show me a counterexample that any one of the axioms fails. What if we were to take and tweak things just a little bit on M22, but instead of doing the trace of U times V, let's do the trace of U transpose V, which gives us U1 V1 plus U2 V2 plus U3 V3 plus U4 V4. Is that going to be an inner product? Again, pause the video, work that one through, and see what you come up with. Okay, so I went ahead and did it as well. So if we look at this, we can push through. It's a little bit of algebra, but that's okay. We can do algebra. And so axiom 1, axiom 2, axiom 3, and axiom 4 all hold. So this is in fact a inner product or an inner product on our vector space M22. And that should not be very much of a surprise because we see that these guys are acting just like vectors in R4, and this looks just like the dot product in R4 does. So just like we did on the front page, but now instead of having 3 components, just with 4 components. So, and we showed in chapter 4 that R4 was in fact also a vector space. So let's try example number 6 here. And so we saw that continuous functions also formed a vector space. It satisfied all 10 axioms. So we're going to let f vector be f of x and g vector be g of x be continuous functions so that they live in this vector space with standard operations. And they're going to be continuous on some interval from a to b inclusive. And we're going to show that f inner product g given by the integral from a to b of f of x times g of x is an inner product. So I'm giving you a hint here, show that it is. We're not asking you whether it is or not, it is. So go ahead and show those 4 axioms on this inner product. And we'll let you work on that and then come back together. So I went ahead and did those as well, using our definition of inner product as the integral from a to b of f of x times g of x dx. We can see that since the order doesn't matter for the multiplication of the functions inside the integral, the first axiom is going to work. By the distributive property, the second axiom is going to work. And because we can factor out constant multiples from integrals, the third axiom works. And the fourth axiom is also going to work because a function times himself, a real value function times himself, is going to give us a real number. And if he's squared, and that real number has to be greater than or equal to 0. And in fact, that will have to be equal to 0 if and only if f of x is always equal to 0. Okay. So one of our primary uses of the inner product is to talk about length or norm of a vector, sometimes referred to as magnitude. And we saw back in chapter 3 that the magnitude of a vector was the square root of the vector dot product himself. But now we're going to take this and generalize it into not just dot products, but any inner product, whether he's an integral or whatever. So we can talk about the distance between two vectors by finding the length of the difference between those two vectors. So I want you to make up two non-trivial vectors in P2, and then using our inner product from number 3 above, which was this guy, looked a lot like the dot product. I want you to find the norm of each vector and the distance between them. So we'll give you a minute to work on that, and I'll make up some non-trivial vectors as well. I'll show you my work in just a minute. Okay, so here's my work. I just picked the x vector being x squared plus x minus 3, the g vector being the function 2x plus 4. Using our inner product, we find out that the magnitude of my f vector is square root of 11. Magnitude of the g vector is square root of 20. And the distance between those two vectors, even though they're functions, is this guy minus this guy. And we'll take the magnitude of the difference vector, which would be 1 squared plus negative 1 squared plus negative 7 squared, 49, 50, 51. So the magnitude would be square root of 51. All right, so we'll pick up there on our next video.